Great, thank you. Everyone can hear me okay?
Yes.
Yeah.
Good. All right. So I'm going to begin by sharing my screen.
Before you share your
Oh,
screen, what
yeah.
is that behind you?
So this is my virtual background. This is one of two 6.5 meter telescopes at our observatory in Chile, Las Campanas.
Ah,
The Magellan telescopes. I believe this is Bada, so it's named after Walter Bada, who I'll actually mention in my talk in not too
okay.
long. All right, so oh, and yeah, I mean, if you guys have any questions, feel free to chime in. I don't know how much I'll be able to see hands raised, like virtual hands raised, and chat while I'm presenting full screen. So, all right, let's share my desktop.
Oh,
All right, everybody see this okay?
yep.
All right.
Yes.
Well, thanks for having me. As Ron said, I work at the Carnegie Observatories, which was also once known as Hale Observatory, and used to be the people in charge of Mount Wilson Observatory. And then up until the 80s, at which point we closed shop there and moved most of our observing to Chile in the southern hemisphere. But of course, today Mount Wilson is run by the Mount Wilson Institute, and I'll be mentioning quite a bit of its history here because this problem with the Hubble constant goes way back. It got started here at Mount Wilson, and it continues. And so I'm going to give you some historical context as well as what's going on now and why it is that you keep hearing that there's a crisis in cosmology. Right. First off, why is it so hard? We've been at this for a very long time. Where the universe came from, how old is it? These are questions that have been asked for a very long time. And you'd think by now we'd have a clear answer. But there's always issues. And the biggest problem really comes down to distance. And this is one of my favorite objects to look at Mount Wilson. So I am also a telescope operator and a volunteer at Mount Wilson as well. And for a certain kind of folks, and I think you guys would probably count as these kinds of folks, we like to show this field. This is the field of 3C273. And when you look at this field, you think, well, okay, I see some stars. In particular, I see one star on the left, and I can tell you that is a star in our galaxy, 25,000 light years away. And okay, that's pretty impressive, 25,000 light years, all right. But then you let the people know that the one right next to it that looks almost identical is a quasar, 3C273, and it is 2 billion light years away. And yet you look at them and there's nothing that tells you one is such a far distance than the other. And this is the problem. We see a two-dimensional slice of the universe, and inferring distance to different things requires different techniques. And I'm going to mention quite a few of them tonight. I don't know how much background everyone has in all of these different things. So if I rush through something too quickly, feel free to stop me. Now, this distance problem came about in what was referred to as the Great Debate. And this great debate was all about this object or objects like it. So it's a faint smudge of a thing off the constellation of Andromeda. And again, you are all amateur astronomers, so I'm sure you know exactly what this is. But at the time, it was referred to as the Andromeda Nebula. And it was one of several different nebulas that had spiral structures, and they referred to them as spiral nebulae. The debate was over how far away this thing was. Is it a thing like our own Milky Way galaxy, as we know today? It is its own galaxy of stars, or is it something close by, maybe a solar system in the process of forming, or something like that? In order to solve this debate, or to bring it to a close, we needed to know the distance, and two big breakthroughs happened that allowed this. One was a sort of an observational technique, and one was just getting a big telescope. So on the left, we have a picture here of Henrietta Leavitt, who was responsible for discovering that Cepheid variables are standard or standardizable candles. I'll explain what that is in a minute. Meanwhile, a little bit later on in Pasadena, George Hale came to this area and decided to build a very large, a solar telescope atop Mount Wilson, and later built some of the largest telescopes the world's ever seen, almost, I think, 4 times in a row. So, what is a standard candle? Well, if you can have something in the universe that you know how bright it is, or how bright it should be, and then you observe it with the telescope and you observe how bright it looks, one thing that lets you do is determine how far away it is. And the reason for that is the brightness of an object goes down as the square of the distance. It's very much akin to the gravitational force. So if I place a star twice as far away from me, then it will look 4 times dimmer. If I put it 4 times further away from me, it will look 16 times dimmer, and so on. And if we had something like, if we could fill the universe with light bulbs that were a standard wattage, and we're able to observe them, then we'd be able to figure out their distances. And it turns out the Cepheid variables are just such a thing. On the left, there is a graph, and I think, can you guys see my pointer when I moved around here?
Yes.
Yes, okay. This is a graph of the brightness of a Cepheid variable, actually 4 of them over time. So up here we have how bright it looks, and on this axis we have time, and they have these characteristic shark fin-like patterns. So the Cepheid gets very bright quickly and then fades more slowly, and it does so again and again with a characteristic period. And this one you can see is just over 40 days, probably 42 days or so. And this one over here is less than 40 days. One over down here is about 22. So they vary with different periods. And what Henrietta Leavitt discovered was that the period was related to how bright the Cepheid was. So a longer period Cepheid was a brighter intrinsically, and a shorter one is dimmer. So if you can determine the period of the Cepheid, then you can figure out in a relative sense which Cepheids are brighter than other Cepheids. And if you can figure out the real distance to a Cepheid and assume they all are the same, that lets you map out the universe. That lets you figure out exactly how far away those stars are. And that's what we did. So a big discovery at Mount Wilson was made with this telescope, which is the 100-inch telescope. And Hubble was one of the astronomers using this telescope, and he was very much interested in this idea of how far away are these spiral nebulas. And he used the telescope to look at not just Andromeda, but Andromeda was the famous one. Oh, did it? Oh, there we go. Okay. So here is a deep exposure of the Andromeda galaxy as we now know it today. And I'm going to zoom in on a particular part and overlay that with this, which is a famous photographic plate that Hubble took using the 100-inch telescope. We're nearing in fact, it had its birthday just recently, but you can see 6 October 1923. So 6 October 2023, we're going to have a little party for it. But this plate is very famous because, as you see, he's written on the plate, and there are these little N's marked here. And these are novae. So these are stars that appeared in the Andromeda Nebula. And we'd known about novae for quite some time. And they happened somewhat randomly over the sky. We weren't quite sure exactly what they were, but they were nothing new. But Hubble was interested in the fact that there were so many in such a small part of the sky. So this area here on the sky is smaller than the size of the moon, and yet it hosted 3 novae, or what we thought were novae. And he was using this as an argument to say this system here, this Andromeda Nebula, must be its own galaxy of stars to host so many novae all at once. However, one of those novae, this one up here, went away as novae do, but then it came back, and then it went away, and then it came back. And so very excitedly, he crossed out the N for nova and put in var for variable. So this is a Cepheid variable. I'm going to zoom in on this now. Depending on how high resolution your screen is and what zoom is doing to the connection, you may or may not see a star here between these two marks. But I will tell you, I've seen this one in person. We have it at the observatories under lock and key in some secret location. And it is very faint. I mean, it's barely noticeable. And in fact, how he discovered that that was there is quite remarkable to me. But let's suppose this galaxy, this Andromeda Nebula, had been inside our own galaxy. And just for as a guess, let's just say we put it at the same distance we are from the center of the Milky Way, which is 8 kiloparsecs. This is what the star would have looked like. So it would have been completely obvious, and you would have had no trouble measuring it. But in fact, it was barely visible. And so remember, this is the biggest telescope in the world at the time. About a 45-minute exposure. Hubble must have known immediately, if this was a Cepheid variable, this tells you this object, this nebula, is very far away. And so the big discovery is that the universe is a lot bigger than was previously thought. Now, that's all just using photographs. That's great, but astronomers have another toolkit, another tool to their toolbox, and that's spectroscopy. And so instead of looking at just a picture of these objects, we can take the light, pass it through a prism or a grating of some kind, and split it up into its component colors. And if you do that for this star, back to this star I was showing you before, you see it's got a sort of a rainbow. This is the rainbow on the bottom to kind of guide your eyes to where the purple light is, where the yellow light is, and the red. So this graph shows how intense the light is of this star as a function of the color of the light that comes from that star, or in more technical terms, the wavelength. So on the bottom here, we have a wavelength in these units called angstroms. Point is, it's brightest here around 5,000 angstroms, which is kind of in the blue. So it's a relatively blue star. And it has these very interesting lines in it. So these are colors that are conspicuously missing from the spectrum. So if I were to draw that in the prism down here below this nice rainbow, you would just see these dark lines. In fact, you might be able to see them in the picture. Again, it depends on how good the resolution is. This is just telling you what kind of elements are in the atmosphere. You've got some sodium, magnesium, calcium, all the good stuff is there. And if we do the same thing for that quasar, you're now going to see something completely different. So clearly this, whatever it is, the physics of this is just completely different than what a star is. For one thing, instead of lines of missing color, you have excess color. So on the right, we have absorption lines, and on the left, we have emission lines. And this usually indicates that you're looking at something much more energetic. And also the width of these lines is telling you that there's some very, very energetic stuff going on here, or some very high velocities. Now, I want to focus on this particular line right here we call H alpha. This is hydrogen, and it's at 60, I always forget what, 67-ish 100 angstroms. But if you look at it with a quasar, it's all the way out here at 7,500. So we expect hydrogen to be at this wavelength, to have this color, and yet in this particular object, it's much redder than it should be. And the reason for this is because this object, this quasar, is going away from us at a significant fraction of the speed of light, about 20%. And that causes what's called a Doppler shift. It's exactly the same thing that happens with sound. So if you ever hear an ambulance that's rushing towards you, it goes nee, 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 nee. And then when it goes past nee, 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 you hear a drop in the pitch. Same thing happens with light. If something is coming toward you at very high velocity, and now we're talking about high compared to the speed of light, the light, it looks bluer. It gets shifted to the blue. Or if it's going away from you, it gets shifted to the red. And this lets us measure how fast something is coming toward us or how fast something is going away from us. So we now have two ingredients. We have distances to things, and we can figure out velocities of things. And so what Hubble, or sorry, I should say Hubble and his assistant, Milton Humason, did was go off and measure a bunch of velocities to galaxies that they could determine the distances to. So here is a graph that's in one of Humason's papers. And on the right here, you've got pictures of the galaxies themselves. We're now going to call them galaxies because we now know that they are actually island universes of stars, just like our own Milky Way galaxy. And here, if you see, it's a negative. So everything that's dark here actually is producing light. And anything that's light in here is actually a dark piece of the spectrum which is missing. And it's not color because these were done on photographic plates. But there are two lines next to each other. These are the calcium H and K lines. This is calcium. And what happens is as you look at these galaxies farther and farther and farther away, these H and K lines are redshifted more and more and more and more. And so this led to the famous Hubble diagram in his 1929 paper. And on this graph, we have distance on this axis. So further along to the right is farther away. And on the y-axis, we have speed either toward or away from us. If the velocity is negative, it's coming toward us. If it's positive, it's going away from us. And I should mention that in this particular diagram, in this year, 1929, none of these velocities were Hubble's velocities. These were all determined by an astronomer by the name of Visto Slipher, who was at Lick Observatory. And the distances, we're often told, oh, well, those distances were all determined with Cepheids, but it's actually not true. Only the Cepheids only get you out to these objects here. After that, the Cepheids are simply too dim because of that inverse square law that I was talking about before. They only get you out as far as these guys. To go further distances, what Hubble did was he assumed that the brightest star in those galaxies was itself a standard candle. So if you have a galaxy or another galaxy, they have lots of stars. Some are dim, some are bright, but you're assuming that the brightest one in each one would be the same luminosity. And so you can use that as a way to try and figure out which galaxies are close, which galaxies are far. So that's how he gets out all the way to here. And the final thing he says in this paper is the outstanding feature, however, is the possibility that the velocity-distance relation may represent the de Sitter effect, and hence that numerical data may be introduced into the discussion of general curvature of space. Clearly, Hubble had been talking to Willem de Sitter, who was a physicist at the time and was working with Einstein's new general theory of relativity. This is a picture of Einstein when he came to visit Carnegie Observatories. If you've ever been to our campus, there's a library and there's a picture of Hale, and that's what you're seeing here. This is the picture of Hale, and there's Einstein. And essentially what he's writing down here is a question. And mathematically, it simply means, is the universe empty? That's one of the things you can do with general relativity. You can say, well, what would happen to a universe that's empty? What would happen to a universe that's full of stuff? And Willem de Sitter, who Hubble obviously had been talking to, contemplated an empty universe. But both he and Einstein wanted a static universe because that's what the universe looked like. We saw stars, we saw galaxies, we saw all kinds of wonderful things out there, but no one ever thought that this whole thing was in any kind of expansion as we know today. And so they were all coming up with solutions to Einstein's relativity that imposed a static universe. Now, some of you may know that Einstein's version of this introduced this thing called the cosmological constant, which was kind of like anti-gravity that balanced the gravity of all the galaxies to keep everything sort of stable, or not stable, but at rest. De Sitter had another way of trying to impose a static universe, which ultimately really failed. But one of the things it predicted was that the further away you were from the center of the universe, and that was the weird thing, his solution had a real center to the universe, a real special place. As you moved away from that center part, things tended to just fly away from you. And it would have given Hubble's result for very close by galaxies. And so I think what was happening was Hubble was talking to De Sitter. He learned about this De Sitter effect, and he said, "Hey, what I'm seeing here might be the De Sitter effect." But it turns out actually that that was not correct. The De Sitter universe ended up being more interesting, but in trying to keep it static, it ended up being non-physical. And in fact, that was pointed out by another physicist by the name of Georges Lemaitre, who was a Belgian priest. And in 1925, he published a note, which I only just recently found. And in that note, it pointed out the problem with De Sitter's universe, that it wasn't quite correct, and that this could explain Visto Slipher's velocities. So he was already thinking about this. But more importantly, in 1927, 2 years before Hubble published his famous Hubble diagram, Lemaitre published a solution to Einstein's equations which showed an expanding universe. And not only that, but an expanding universe would show exactly what Hubble had seen. And he even went as far as determining the first Hubble constant at 625 kilometers per megaparsec. And I'll tell you about what those units mean in a minute. Later on, he was asked to translate this into English because the first publication was in French, and so probably is why it wasn't noticed as much by the American astronomers working at Mount Wilson. And he republished his paper in the monthly notices of the Royal Astronomical Society, but interestingly enough, his value of the Hubble constant was missing from that republication, and there was all this conspiracy theory going on that Hubble had somehow influenced the editors to keep it out. But it turns out there was a letter from Lemaitre to the editors that said essentially, "I'm not going to put it in because Hubble's value is better." So if you ever heard of that controversy, there actually really isn't any conspiracy from Hubble or anything like that. It was just Lemaitre being pretty much humble. So just to give you an idea as to why an expanding universe works for this, here's a sort of a play universe. It's just the Hubble deep field in black and white. And what I can do with the magic of Keynote here is I can just expand it. All right, so it's almost like putting it in a photocopier and expanding by 10%. That's really just what I did here. And now I'm going to make this one transparent so you can see the old one underneath. And what you're imagining is between both of these times, some time has passed in the universe, and in that time it has expanded. And we live here in the center. And what you can see is that if I look at a galaxy close by, it's moved by, this much. So it's going at a relatively small speed. But if I go further out, and look at this galaxy, you can see it's gone quite a bit further in that time period. And it just means that the farther away a galaxy is from you, the more space there is between you. So there's more space growing, and therefore the thing gets pushed away a little faster. So in this universe, in this interpretation of Einstein's field, Einstein's gravity, it's not the galaxies moving through space. It's space itself growing in between them and pulling them along for the ride. Okay. And this explains Hubble's law, right? The further away you are, the faster the galaxies appear to be moving away from you. And therefore you get his famous graph. But more importantly, if I choose any other galaxy, like this one over here, and now I'm at this point, so everything is relative to me here, you can see that I see exactly the same thing. All the galaxies are moving away from me, and the farther away they are from my point of view, the faster they are moving away from me. So it fixes two things. It gives me Hubble's law, but it also fixes this uncomfortable notion that somehow we're at the center. Everything's moving away from us. But actually, it's true for everybody. So every point is moving away from every other point, or every point in the universe appears to be the center of the expansion. So that makes us much, much more happy. And if you turn the clock back and you say, well, the universe is expanding now, things are getting farther and farther, it means they must have been closer and closer in the past. And in fact, if you move it all the way back, they must have all been in the same place at time zero. And Lemaitre referred to this as the cosmic atom. But for us, the practical upshot of that is if you take the slope of this graph, which will have units of kilometers per second per megaparsec, right? So the vertical axis is in kilometers a second, even though the per second is missing from the graph. And on the x-axis, he's got 10 to the 6 parsecs, but we just call that a megaparsec. Then the slope is kilometers a second per megaparsec. And if you take 978 divided by that slope, that will give you the age of the universe. So the larger the Hubble constant is, the younger the universe is, and vice versa. So determining the slope of this graph, the Hubble constant, as we call it today, allows you to essentially measure the age of the universe, which is very important for cosmology. And it's changed over the years, not because the universe's age has changed, but because our observational techniques have changed. So the initial values of the Hubble constant were all up here in the hundreds, the 500, 600 range, something like that. And if you go back to that little formula I put down, well, if you take 980-ish and divide it by something like 500, you're only talking about something like 2 billion years. And that's uncomfortably young, given that the Earth is 4 billion years old. So there's a problem here. And the problem was that Hubble didn't realize there were two kinds of Cepheid variables in the universe. That was discovered by Walter Baade in about the late 1950s. Again, a Carnegie astronomer working at Mount Wilson, he discovered there were two populations of Cepheids. And when you take that into account, all of a sudden, all your distances are now different. They essentially go up by a factor of 2, which means the Hubble constant goes down by a factor of 2, almost. And now you're in this regime where we were in the 60s, the 70s, the 80s, basically bouncing around between about 50 and 100 kilometers per second per megaparsec. Another Carnegie astronomer by the name of Alan Sandage, very interested in the Hubble constant. He was kind of Hubble's student, his protege, and he continued working on the Hubble constant for the rest of his life. And he was very much convinced that it was on the low end. It was in the 50s. He even went so far as to have a vanity license plate made, which said H050 on his car. But it's almost like it was a small mini debate, right? We had solved the debate about how big the universe was in terms of galaxies, but the Hubble constant now tells us, is it a young universe or is it a slightly older universe? And so that actually became something of a great debate. Maybe a minor debate. Anyway, there's lots more history to this, but you can learn more from the Mount Wilson webpage if you wish. I put the webpage up there if you want to go have a look. Also, I'm sure you guys know this, but you can rent out the telescopes. So you could, in fact, get a group together and go observe on the 100-inch telescope, on the same telescope that observed the distance to the Andromeda galaxy and discover the expanding universe. All right, how about nowadays? Well, it turns out we're still at it. If you had been watching Jeopardy one particular night, you would have seen this question, which came up, and that Wendy Friedman et al. Nailed down the value of this man's constant, which with distance helps find the velocity of galaxies. Actually, that's not correct. We can determine the velocities of galaxies just fine, thank you very much. It's that which allows us to then figure out the distances. But anyway, they got it backwards, but that's okay. But it still shows you that this is in the public consciousness if it makes it onto the Jeopardy questions. And so if you don't know who Wendy Friedman is, Wendy Friedman started as a Carnegie Fellow at the Carnegie Observatories. She then went on to become a staff member and was also the director of Carnegie Observatories. More importantly, she was the principal investigator of the Hubble Space Telescope Key Project to measure the Hubble constant. That's a lot of Hubbles. So Hubble Space Telescope obviously is named after Edwin Hubble, but it was also essentially had a bunch of key projects that were going to be the big discoveries it was supposed to make. And one of those was to actually nail down the value of the Hubble constant once and for all. And so Wendy was the PI for this. And of course, there's a lot of people who worked on the project. But her paper in 2001 essentially put this to bed, essentially, in terms of, is it 50? Is it 100? Well, guess what? It's exactly halfway between. It's 75 with, a healthy error bar to it. And again, this is doing exactly what Hubble was doing, measuring velocities of the galaxies, measuring distances using Cepheids. The difference is they got to go further out. So in blue here, I've put the limits of Hubble's original diagram from 1929. And it may not look like you've made all that much progress, but remember, he only was able to go out this far using Cepheids. All the rest of those distances were using another technique, which actually is not nearly as reliable. So Hubble allowed you to go all the way out here using Cepheid variables. And that's because its collecting power was comparable to that of the 100-inch, but it's in outer space. And so it has no problems with the atmosphere blurring the image. And so it can get these very nice sharp images of these galaxies, and you can see those Cepheids. Okay. Oh, sorry. Actually, I should point out one more thing. You may notice that one thing that's different about this graph from Hubble's original is there are error bars on the points, these little lines here that give us an idea of how certain we are about these points. So we've measured, in this particular case, a distance of, let's see, something on the order of 18 or so megaparsecs and about 500 kilometers a second. But we have a certain uncertainty in those values. We're not completely confident that that's the actual value. And this gives you an idea of how much play we have. And you may notice that, hey, we've got quite a bit of uncertainty in the velocities, which at first looks kind of strange. Why would we have uncertainty in the velocities more so than uncertainty in the distances? Because distances are harder to measure than velocities. Well, yes, but the interpretation of the velocity is a little tricky. And so here's Stefan's quintet, always a nice one to look at. These are galaxies that are gravitationally associated with each other. So imagine that as a whole, this grouping of galaxies is moving with the Hubble expansion in that direction. I guess we're down here somewhere. And it's going with a certain velocity that you would expect from Hubble's law because of the expansion of the universe. The thing is, because all these galaxies are pulling on each other with their own gravity, they have their own motions in this group. Imagine if you had a jar of fireflies, you can move that jar around, but inside the jar, those fireflies are buzzing around in all kinds of different directions. So if I measure any one of these galaxies, the velocity could be added together. So these could add up and I'd get a larger Hubble expansion than I expected. Or if the galaxy is coming towards me like this, that has to be removed from this total velocity. So all these arrows have to be added up. And so these are not known to us, and therefore we must count them towards our uncertainty. To solve this, because that's what we really want to do, we want to make this better, we need to go farther away, because the farther away we go, the larger we expect the Hubble expansion velocity to be, whereas these will all stay around the same. This is just the gravity of a group of galaxies. They don't get larger as they get farther away from us. It's the expansion of the Hubble, it's the expansion of the universe that's causing this to get larger. So we want to go farther away. The problem is, even with Hubble, you can only go so far. And that's because if you look at the images of these galaxies really close up, you can see here are these Cepheid variables that have been identified in the field, but there's all kinds of other stars in there as well. And isolating the light of this from everything else is hard, because those other stars are going to add light in towards where you're trying to measure it. And as you get farther and farther away, that gets harder and harder and harder. Everything appears to get closer together from our perspective. And so it's harder and harder to get that light of those Cepheids uncontaminated from all the rest of the light of those galaxies. So what we really need is either a better telescope, which I'll talk about at the end, or a better standard candle. and preferably something brighter than Cepheids. That would also be nice. And it turns out there is such a thing. And that's a type 1a supernova. And a type 1a supernova is a particular kind of a supernova, which is an exploding star. And what we believe happens with a type 1a is that you have this white dwarf, which is the end of a star's life. So at some point, there were two big stars in this system. One runs out of fuel, compresses down, and the core remains, and the outer atmosphere has blown away, leaving this hot, dense core. But it's in close proximity to a companion, and it's allowed, the gravity lets it sort of suck out a little bit of that material, and it builds up and builds up and builds up until it gets to a magic place called the Chandrasekhar limit, and it basically just blows itself up. And the physics of this is actually really interesting. It involves quantum mechanics and statistical mechanics and all kinds of wonderful things I don't have time to get into. But let me just say, it's a magic mass that if it gets to that mass, it will blow up. And so you can imagine that that kind of sounds like a standard candle, right? If it's always sort of slowly building up to this magic mass, and then it blows up, maybe there's a hope that this would always be the same brightness, no matter where it is in the universe. So here's a little movie. If you've ever used this, this is a fun thing I just discovered called Space Engine, which is a kind of a planetarium software, but it allows you to move anywhere you want in the universe. And if it has the data, it will show you the data. So I decided to go looking for one of my favorite type 1a supernovas. So here we go, we're going to zoom in. This is sort of simulating what it would be like to zoom in with a telescope. And so you're seeing more and more and more and more stars. And then you get to this galaxy. And in there is a supernova that went off. But you might not be able to tell which it is. So if we leave the galaxy, which you can do in Space Engine, now you can see all those stars that were there before. Those were just stars in our own Milky Way galaxy. We aren't interested in them. And if you were able to leave the Milky Way, then you would see this galaxy and you would see that supernova sitting right there. So on the face of it, sometimes you look at these supernovas and they don't look all that, incredibly bright like you'd expect. But remember that this is an entire galaxy. All the stars in here are just sort of faint and you can't really see them. But that one star that blew up, it's very noticeable. And then over the course of about a month or 2 months, it will slowly fade away. And then you can come back and you can re-observe this galaxy without the supernova there. Here's the actual image of that supernova. This is supernova 2012 FR in the galaxy of NGC 1365. It's in the southern hemisphere. Beautiful galaxy. I love it. And we observe this supernova a lot. But the important point is not only is a supernova bright, but it goes away. Like Cepheids never go away. They're always there. They're just getting brighter and dimmer and brighter and dimmer. But a supernova actually fades away. And so if you have your main observing here, like we have one night, there's a supernova somewhere in this image. This is another kind of galaxy called an elliptical galaxy. And then you come back a few years later and measure the same field again. Now, because it's a digital image, you can just go and subtract one from the other. And you're left with the supernova all by itself. And this is really clean. I can measure the brightness of that object very easily without any other contaminating starlight because it's all been subtracted out from that other image. And so this is another supernova, 2011 IV. And interestingly enough, we also had another one in there in 2007 ON. We just happened to use the image of the supernova when we were studying 2007 ON. We had that already on our computers. And then when 11 IV happened, we're like, oh, hey, we can just use that same image. We don't have to wait this time. But that's why it shows up being white. Oh, and again, this is a negative. So dark means bright. And this means this is a negative flux. And that's just because that supernova was there from previous years. This is how they behave. there's a little movie at the lower left from ESO. It just shows you that supernova going off and then sort of fading away. And it does it in a very characteristic way. It rises very quickly, just like a Cepheid, reaches some peak, and then falls off with some characteristic timescale. And just like Cepheids have different timescales, right? We have Cepheids that pulsate on a short timescale, and we have Cepheids that pulsate on a long timescale. We have supernova type 1As that get bright and then fade away slowly, and ones that get bright and fade away quickly. Also, a characteristic of a type 1A supernova is if you look in the infrared, you actually get two peaks. So it gets bright, dims, then gets bright again, and dims back down. And another fun fact, all the light you see from a type 1A supernova is the result of radioactive decay. So these supernovae, they do nucleosynthesis all the way up to nickel 56, and then that nickel 56 decays to cobalt 56 and liberates energy, just like a nuclear reactor. And the cobalt 56 decays to iron 56, and we often refer to type 1As as iron bombs. So probably the vast majority of the iron in your blood comes from a type 1A supernova. They are very efficient at generating iron and iron group elements. But just like Cepheids, it turns out, and this was discovered by another Carnegie astronomer, this is Mark Phillips, if you plot how bright the type 1A supernova is against how long it lasts, so that's on the right, the x-axis here, there's a slight trend. So the longer it lasts, the brighter it is. And we have to take that into account, just like we do with Cepheids. But more importantly, it turns out, and this is true of Cepheids too, I just didn't mention it, the redder the objects are, the dimmer they tend to be. And by red, I mean you look at the supernova in a blue filter and you look at the supernova in a red filter and you compare the two of them, that gives you an idea of how red it is. If it's brighter in the blue and dimmer in the red, well, it's a blue supernova. Otherwise, if it's dimmer in the blue but brighter in the red, then you can call it a red supernova. And you can put a number on that, and you can see there's a very strong effect of the color on how bright the type 1A is. And this is basically interstellar dust. This is that stuff that makes the Milky Way have those dark lanes in it. We are looking at the same kind of stuff in these other galaxies that host these supernovae, and the redder they are, the more dust there is, and we have to take that into account. Because what we're really interested in is the distance. The distance makes things dimmer. So anything else that makes things dimmer, we need to take that into account. Otherwise, we're going to mistake it as a distance, right? So if we weren't taking this into account, we might mistake this supernova over here as very far away compared to these ones. But in fact, it might be the same distance, but it's just red. And so it has this interstellar reddening and making it artificially dim. So these are things we have to do. However, if you work in the infrared, or in this case, the near infrared, you can do the same trick, same experiment. And you may notice that this one is a lot flatter. There's a lot less of an effect on how long they last. And a much smaller effect on how the dust affects them. And that's because the way interstellar dust works is it preferentially absorbs bluer light. So the redder the light is that you're working with, the more you see the original brightness of the supernova. So in the near infrared, these guys are almost nearly perfect standard candles. We still, measure how red they get, and we measure how long they last and things like that. But the effects are much smaller, so they're much easier to use as standard candles. Unfortunately, we still need to work with Cepheids. And the reason for that is because the inverse square law always gives me a relative distance. I can say, hey, if that supernova is twice as far, it's 4 times as dim. But it still means I need to figure out how far the closest one is. And then once I do that, I can set the scale, and now I can do the work to get all the rest of them. And there hasn't been a type 1A supernova in our galaxy since I think Kepler observed one in 1600 and some. So we're way overdue. Galaxies tend to give out type 1As on the order of 100 years or so. And so it's been 400 years, and we're very much ready to observe one of these, but We don't. So we don't have any type 1a supernovae that we can measure the distance to independently. And so we need to rely on a different technique, and that is for nearby things like stars, we can use parallax. There's a satellite out there called the Gaia satellite, which is very good at measuring distances using parallax. And this is just a triangulation technique. You basically look at a star at one time of the year and then wait for the Earth to go around the other side of the sun, look at the star at the different time of year, and that makes the star appear to wobble back and forth if it's close by compared to other stars. And that's just geometry. So we can use that to figure out parallax very easily. That gets us out to about 4 kiloparsecs in our galaxy. Using that, you can figure out the distances to the closest Cepheid variables. And now you know how bright Cepheids are. And you also use Leavitt's law, Henrietta Leavitt's law, and that gets you further out. And then you can use those to figure out the distances to galaxies where a type 1a supernova has gone off. And now you know how bright the type 1a supernovae are. This whole way of building out farther and farther and farther, establishing how bright things are and using them as standard candles is referred to as the distance ladder. And it is a rickety ladder. Any rung in that ladder, if something changes, if you discover, for instance, when Hubble didn't know there were 2 kinds of Cepheids, then changing any rung means everything above has to be rescaled. So we have to take all our distances with a little bit of grain of salt and try to do the best we can. So we started a group that we called the Carnegie Supernova Project back in 2004. That's when I actually got to Carnegie as a postdoc. So here I am, all young, bright-eyed and bushy-tailed. Wendy Friedman, she was a member of the group as well. Mark Phillips, who had made the discovery about type 1a supernovae, and so many other people. And one person I really do want to point out is this person here. This is Nydia Morel. And Nydia is an astronomer. She observes everything on all our telescopes at Las Campanas. And whenever someone needs to know how an instrument works, she knows how it works. And she does a lot of the observing that allows the science that I'm going to show you next. And I have a story about her in a little bit. And of course, things change. We have more people come along, some people leave. And another person I want to point out is this young man here. This is Shuvo Uden, who is, or I should say was my postdoc for a few years. He's now at Texas A&M. And he did a lot of the work that I'm going to show as well. So it takes a village. I get to, talk to you about all these great discoveries, but please keep in mind there are, on the order of 25 to 30 people behind all this. And we need every single person to get this done. So the C in CSP, Carnegie Supernova Project, you could say it's Carnegie, but also it could be Chile, or it could be Campanas, because Las Campanas is the observatory where all this happened. And I'm just going to highlight a few telescopes. Over here, we have the twin Magellan telescopes, 6.5 meters. This is what I have as my background here. That's one of them. And then we have the DuPont telescope, which is a 100-inch telescope here. And the Swope telescope, my favorite, which is just over here, which is a 40-inch telescope. And this is what it looked like a couple of days ago. So you can see that we got some snow and some interesting weather going on. It's winter currently down in the Southern Hemisphere, of course. And I got this just today. So there will be no observing tonight. There will be no new supernovae discovered. We are closed for weather, unfortunately. But when we do observe, the 40-inch does a lot of the lion's share of the observing of the supernova in terms of how bright it gets. So here's just a collage of galaxies. And unfortunately, the resolution may be a little low, but in each of these, believe me, there is a supernova that has been measured. And then we use the 100-inch telescope, the DuPont, to get spectra. So we still need spectroscopy of the galaxies and of the supernovae. We have to make sure they're type 1As, and that can be done most easily through spectroscopy. And you need a bigger telescope. When you take that light of a star and you spread it out using a prism or a grating, it means you're going to make it all dimmer in all those different wavelengths. And so you usually need a bigger telescope to do spectroscopy than you do to do what we call photometry, which is to take the picture. Okay, so here's the original, well, not the original, sorry. Here's the Hubble Space Telescope Key Project version of the Hubble diagram that I showed you before. And just to give you an idea how much better we can do with type 1a supernovae, that's how far we get out with type 1a's. However, this particular Hubble diagram is a little out of date. This is from a paper I wrote back in 2018. So I'll put in the values of the Hubble constant I got for those. And yeah, so 73, it's a little lower than 75, but you may notice that the error bars have shrunk substantially. But even that is now out of date because we started a new campaign to go even further out. And so here, that goes, just to give you an idea, that the most distant object we looked at was 1 billion light years away. And now, this is how far we are. So we've gone about twice as far using better CCD cameras and also a larger telescope. So now we've moved our primary observing onto the 100-inch DuPont telescope. And there it is. That is our Hubble diagram. I am not going to put the value of the Hubble constant on because we're not quite done yet, and I'm not going to put my neck out. But there is a fit using a regular Hubble law, right? Just a nice straight line with a slope. And you may notice that it's not quite working, right? We seem to do okay down here, but as we get up here, these points seem to be going systematically to the right or maybe down. And the reason for that is because we are looking so far away that we are looking far enough into the past. So that's one thing you got to remember about astronomy. Every time you look at something, you're seeing it as it was in the past, and the further away it is, the further into the past you're looking. We're looking so far into the past that actually the Hubble constant was not the same as it is today. You may have heard that the universe is accelerating. So in the past, it was expanding at a slower rate than it is today. And if you take that into account, this is the line you get. So as you can see, we're now going far enough out that we're starting to measure the effects of real cosmology, which is not just how fast is the universe growing today, but how fast was it growing in the past. So you'd think, well, that's great. We're getting a good value. Everything's making sense, right? But we keep hearing about this thing called the cosmic crisis or the crisis in cosmology. So where's that coming from? Well, it's coming from this other experiment, and this is the Planck satellite. So the Planck satellite, which came after the WMAP, measures the cosmic microwave background. This is essentially an infant image of our universe back when it was so hot that light couldn't travel very far, and then it became cool, and the light was allowed to leave there to get to us, but left behind these signatures. And this shows us where the universe was hot and cold when it was only 111,000 years old. And so what can you do with that? Well, if I go on this map and I find every little hot spot and I cut out that hot spot, and then I find the next hot spot and I put it on top of that, and I get another hot spot and put it on top of that, another hot spot and put it on, and I take an average over all those hot spots, you get a pattern that looks like this. You could also do the same thing with the cold spots. And what you can see is that there's a hot part and then a cool part, and then it gets hot again, but it's got a very characteristic size to it. This has to do with how the gas was expanding. It's a plasma, and this plasma was expanding and contracting. So the heat was causing the gas to grow, but gravity was trying to bring it back down again. So you had almost kind of this ringing effect. And what you're seeing with this ring is essentially the fundamental mode of this oscillation in the early plasma. And the cool thing is that's all physics. If you know the temperature, the density, and all that sort of stuff, there's physical equations that tell you what that size should be in light years, megaparsecs, whatever. And we can measure that angle on the sky with a high degree of accuracy. And that gives us what's called a standard ruler. It's like a standard candle, but instead of going down as the inverse square, standard rulers go down as 1 over the distance. And if you use that physics and you measure that angle, you can now get a Hubble constant from the cosmic microwave background. So this is completely independent of anything else I've just told you about. And they get a value of 67.6 plus or minus a tiny little 0.4 kilometers per second per megaparsec. So they claim to have measured this with insane accuracy. And this is the cause of the crisis. This is the cause of the tension. But you got to keep in mind that the cosmic microwave background happened at the very beginning of, or near the very beginning of the universe. And so all that light has to travel through all the history of the universe, through galaxy clusters and everything else before it reaches us. And so an interesting idea is that if they're getting a different answer than we get locally, maybe there's something wrong with our model of how the universe expanded or what it's made of or something like that. So this is why a lot of folks are claiming that this is a reason that we might have new physics. Maybe Einstein's field equations need to be updated. Maybe we don't know everything about dark energy or dark matter, something like that. So what we really want to do is we want to figure out, how is this real? Is there a real difference between the cosmic microwave background value of 67 and what we get locally, which is around 75? One of the things you'd like to do is test all your different steps along the way. And one of the big ones for us is the Cepheid variables. Maybe we're doing the same thing Hubble did. Maybe there's a problem with the Cepheids that we just don't understand. So it'd be nice to be able to replace them with something else. And there are a number of things you can do. And this one is called the tip of the red giant branch. It was pioneered by another Carnegie astronomer, Barry Medor. And what you do here is, it's kind of like what Hubble did with the brightest star method in his galaxy. But in this case, you're actually looking for a particular kind of star, and that's evolved stars which are on what's called the red giant branch. And this is stars after they run out of hydrogen and start burning helium, they start going up this thing called the red giant branch. And they reach a certain brightness, which is well defined and is understood with physics. And here is what, just showing you what it looks like. So we have here, these are all stars. So every single dot on this graph is a star, and they all come from a Hubble Space Telescope image near this other galaxy. You may remember seeing this galaxy before. And when you plot how red they are versus how bright they are, you get this nice locus of stars with a definitive tip to it. And you say that tip is going to be at the same brightness for all galaxies. So no matter what kind of galaxy I have, I think stars behave exactly the same way. They all go up this red giant branch. They all reach a maximum. And if I can measure where that is from galaxy to galaxy to galaxy, I can get a relative idea of how far away they are. Because another galaxy, which is further away, would have this tip lower down. Okay. So that's what we do. We take this good old distance ladder, take out the Cepheids, put in the tip of the red giant branch, and redo the experiment. Now, what kind of Hubble constant do we get out of that? And here's just a graph of essentially the state of the art over the last, couple of decades. Up here, we've got the Wendy's paper from 2001, the Hubble Space Telescope Key Project, which got 75 plus or minus 10%. So it's, that was the state of the art at that point. Here's a paper that I wrote that I showed you before, where we got something on the order of 73. Another group, which Adam Rees, who is the person who's been doing the most work in this particular field. We were kind of essentially in some ways only doing a check on what Adam had done. You also may know Adam Rees as being one of the recipients of the Nobel Prize for the discovery of dark energy. And we get the same value, which is good. With a slightly larger error bar. We considered a few more sources of error than they did, but essentially we're pretty much consistent. And down here is that cosmic microwave background value. Okay, so all along here is what value of the Hubble constant are you? and this is just ordering them in some way. And this is the source of the tension, right? I have a very small error bar here, which is inconsistent with the value here and its error bar. There's a gulf between these points, which may or may not be significant and may or may not indicate new physics. Well, okay, let's put in this new value with the tip of the red giant branch instead of using Cepheids. Well, it came over this way. And it kind of ended up halfway, which didn't make anybody happy. And you can do this again with other techniques besides the tip of the red giant branch. There's another one called surface brightness fluctuations. Again, sort of somewhat low, but strangely, there are other ones. You can use gravitational lenses to measure Hubble's constant. They get up here, but using the exact same technique, another group got down here. And just recently, someone else did a surface brightness fluctuation analysis, and they ended. Oh, sorry, wait, no. Right, there's also gravitational waves. They let you do it as well. And then most recently is this one from 2022, which uses surface brightness fluctuations and ended up all the way over here. So it's all over the place. Unfortunately, I don't have many more points to show you for the cosmic microwave background, but they've done everything they can to try and move that point over to join these guys, and there simply isn't any way for them to have any wiggle room. The measurement is just so precise. We've decided to do another analysis. This is what my postdoc is doing, or my former postdoc is doing right now. So he will hopefully be publishing this in 2022. And essentially doing the same, but combining all three. Combine the Cepheids, the TRGB, and the tip of the red giant branch, and the surface brightness fluctuations. Put them all together and see if you can make them behave and what value you get. And unsurprisingly, you get something kind of in the middle with a much larger error bar. So this is what we'll be publishing, but I'm not going to tell you exactly what that is because we're not exactly sure that we have the right value just yet. But point is, it kind of gets down to where the cosmic microwave background values are, but still it's uncomfortably far away. So I don't think we've identified everything that could be wrong, but it certainly seems to me that given how much scatter there is, oops, I'm sorry, I went backwards instead of forwards. Given how much scatter there is in these points, it really does point to some kind of systematic error with the local values. All right, that's that. Trying to, oh, interestingly, I got my there. Okay, so just to finish up, what we really need to do to answer the question, is this tension between the cosmic microwave background and the local value of the Hubble constant, is it real? Is it something interesting? We really need to sharpen up the distances locally. And that's going to be done by, right now, James Webb Space Telescope. And in the near, I hope, future, the next generation of giant telescopes. This one shown here is the Giant Magellan Telescope. Carnegie is one of the founding members of this project. But Caltech has one as well, which is the 30-meter telescope, and the Europeans are in the process of building their own. So what does this let us do? Well, I hope at this point you guys have all looked at those James Webb Space Telescope images as much as I have. This here is, I believe, a Hubble Space Telescope image of back to good old Stephan's quintet. And if I now go to what the Webb sees with this, okay, there are differences, but I'm going to zoom in on one of that galaxy, this galaxy right here, because I think there's something interesting that you want to see here. So again, this is the Hubble version. And what I'm hoping you see is many more stars, many more individual stars sort of pop out. I'm going to go back again and just sort of go back and forth. Its larger aperture means that it has a sharper image, which means those stars are now more point-like than even with the Hubble Space Telescope. So when you identify the Cepheids, it's easier to measure their brightness and not be contaminated by all the light from the rest of the stars in the galaxy. It's still a problem, it's still hard to work, but it's easier and hopefully less prone to errors. The other thing that I find great when I look at this image is if you go back to Hubble and you see these dark areas, that's that interstellar dust I was mentioning before. So, if a supernova happens behind one of those, then it's going to be dimmed by this dust. But in the mid-infrared, which is what Webb is doing, it's all an emission, which means that dust, in absorbing all that optical light, well, that dust heats up and it re-radiates the light, but now in the mid-infrared rather than in the optical. And so this presents another interesting problem. Instead of worrying about whether your galaxy has dimmed your supernova, now you might have to worry about excess emission from the dust. But the good news is, with supernova, that's not a problem because we just subtract all this away and it's fine. Okay, so is the tension real? Oh, and I should also mention one of the projects that the James Webb Space Telescope is going to be doing is led by Wendy Friedman, and she and her group, and I'm sort of in that group a little bit, they intend to measure Cepheids in galaxies like this and also measure the tip of the red giant branch all at the same time. And therefore, they can make a direct comparison between the distance that the Cepheids give us for that galaxy and the distance that the tip of the red giant branch gives us for that galaxy. And that will let us determine, is one of them right? Is one of them wrong? Do they come up with the same answer? If not, what do we do then? But it gives us an idea of how much uncertainty there is in these distances using these different techniques. So to wrap it all up, is the tension real? Is this new physics a possibility? I don't know yet. I'm hoping that this project that Wendy is doing with the simultaneous tip of the red giant branch and Cepheid distances using James Webb will help determine the local systematic errors and give us a good idea of what those are so that we can confidently put our error bars in place. Let's suppose it is real. Is it new physics? Maybe, but Occam's razor is pretty sharp. If you're going to introduce new physics, you've got to have some really compelling evidence to do that. And while it's interesting, this does not raise to the level of that kind of evidence to put in new physics. And folks have tried to put in new physics and they've not come up with anything that makes everything work. So could be, but my gut feeling is probably not. We've been here many times. Back when Hubble first had his very large value of the Hubble constant, and we had this problem of stars in the universe that are older than the universe because the value of the Hubble constant is too large. Every now and then when that happens, people pull up the cosmological constant and try to use it as a way to justify why we have this difference. And even though we seem to have a cosmological constant these days with the accelerating universe, every time we've ended up with a problem like this, we try to introduce new physics and then we find, oops, it was something we just didn't know about Cepheids. It was something we miscalculated with, whatever. So my gut feeling is that no, this isn't really new physics, but only time will tell. And gravitational waves will probably settle it for good. I didn't have time to go into how gravitational waves work, but essentially, when you have a neutron star and a neutron star merging and they produce gravitational waves, and you can measure that with something like LIGO, you can get the distance to that without any standard candles. It's all just a physics equation. There's no Cepheids, there's no parallax. You completely bypass the distance ladder. You have a direct measure of the distance, and then if you have a velocity, if you can figure out where it happened in what galaxy, then you have essentially solved the problem. Now they have one such case that you saw in the diagram I had before, but the problem with that one was it was so close by that velocity was not a good velocity to measure the expansion rate. It was just too close by. So we need a gravitational wave source that's farther away. And it's my hope that something like that will happen in the near future, and then we'll know for sure what's going on. But until then, well, keep posted, and thank you for listening, and I'm happy to answer any questions. And sorry
You
for going a
go,
little long.
are you going back to Chile soon?
Oh goodness, am I going back to Chile soon? I would love to go back to Chile soon. Right now, we are in what they refer to as phase 3, which means only astronomers that are already at the observatory are allowed to go up to the mountain. They don't want to have any kind of outbreak happen on the mountain when you're so isolated away from uh, medical resources. So for now, we are observing on the telescope. Sorry, on the computer. We zoom with our telescope operators, and we can remotely access the computers that run the instruments, and we do the observations that way. And the interesting thing is, I think a lot of astronomers are actually getting to like this. It's 24 hours of straight travel to get from here to Chile, and it's lovely to be down there, but it's a lot of travel. So it wouldn't surprise me if this whole remote observing thing continues even after COVID's over.
Is there any benefit to actually being in Chile?
There is a benefit. One is the internet connection to the mountain isn't the most reliable thing in the world. So if your internet connection drops, it's just like being clouded out. So there's that. Um, if you're at the site, it's much easier for you to if one part of the sky is not behaving, it's got some clouds or whatever, then you can get a bird's eye view and you can see exactly what's going on, and you can redirect your program to somewhere else. It's getting better and better. I mean, they've got now an all sky camera that can show you what the sky looks like. So it's almost like being there, but they love having us as well. I mean, if it's only the staff astronomers at the observatory, they like having visitors come down because they get to learn about all the new stuff that's going on. So there's a social aspect to that as well. But yeah, it's better to be down there just because then you don't get internet connections that drop out. And oops, sorry, forgot to turn off my alarm.
I have a question.
Could it,
Oh, go ahead, Ron.
go ahead. No, well, all right. Could the discrepancy between the value for the Hubble constant that's measured with the cosmic background radiation, could that be caused by, like you were saying earlier, just the value having been different that long ago?
Oh, no. So that's what happens. So yeah, when you measure the value at the cosmic microwave background, you get something completely different. And then what you have to do is you have to use Einstein's equations. Well, actually, Einstein and Friedmann's equations to then say, if that's how I measure the Hubble constant at the cosmic microwave background, I then have to bring that forward to where we are today and say, what would I measure now? And that's why I sort of mentioned that you have to figure out exactly what's between you and the cosmic microwave background. You need to know how much matter there is in the universe, how much dark energy, dark matter, all that sort of stuff, because then that lets you take the Hubble constant as measured at the cosmic microwave background and bring it to today and compare with what we measure today. So that's where the new physics could come in. If there's some massive neutrino or something out there that you don't know about, then that procedure of taking the cosmic microwave background Hubble constant and bringing it forward, you're going to get the wrong answer. But they take that into account. That idea that you're measuring a different Hubble constant in the past, that's taken into account, and you still end up with this tension.
Chris, can I ask, when you're looking at the Cepheid variables in Stefan's quintet, don't you need a lot of observing time on the DWST to collect the data you need?
Yeah, you
Like
do.
multiple days, right?
Multiple days. You have to have not only to measure the period, but you have to find them in the first place. So you have to take snapshots of the galaxy. You have to find variables. You have to identify the Cepheid variables in those, and then yeah, you gotta measure a period out of that. That is one of the advantages that the tip of the red giant branch has, is that you only need one snapshot. You just need to measure the colors of the stars and how bright they are, and that lets you make that diagram. The other advantage of that is Cepheids tend to be in the disk of the galaxy. They tend to be in young populations, so where the densest stars are, whereas tip of the red giant branch, you can do it almost anywhere in the galaxy. So they tend to do it in the halo, where the star density is a lot less, and so you have less problems with measuring the brightnesses of those stars. So yeah, you're right. It is it is expensive, that's for sure.
Well, that kind of leads to another question, which is sort of unrelated. I hope you don't mind me asking. The funding for the Carnegie Institute, is that really just going back to Carnegie? I mean, did he
Oh.
give enough money to keep it going forever?
No, alas. So in the good old days, back in the time of Sandage and the rest, you were actually not allowed to go and seek granting information grants from any other institution, because they considered the time it would take for you to go and apply for grants to be a waste of time, and the endowment was large enough to sort of run everything. Today, yeah, no, we still have an endowment, but it is not nearly enough to cover all the expenses. Just this telescope behind me, that could not be financed entirely with our endowment. We actually we run this as a consortium amongst Carnegie and a bunch of other institutions, all pooling resources together. So as a researcher, a certain amount of money I can get on the endowment, but for a full-blown research project like the Carnegie Supernova Project, we required National Science Foundation money. So we applied for the grants, and we were granted money, so we were able to do the project. It's a good question, though. It would be nice if we didn't have to apply for grants, but that's the reality.
I have a question also, and it's very similar to, I think, what Ron had asked before, and you may have answered it, but let me pose it to you. It would seem to me that it would be kind of interesting, to me at least, if you were to take all these supernova type 1A measurements and put them in bins, so that you would be able to come up with your best estimate of the Hubble constant for, let's say, super 1A or supernova type 1A A's that occurred between here and 2 billion light years away. Do the same thing for 2 billion light years to 5 billion, and 5 billion to 8 billion, and 8 billion to 11 billion. I think it would be kind of neat to see a plot like that, to see how the Hubble constant, which changes by distance.
So in fact, that is exactly what we do. We like to show these nice Hubble diagrams, because it just shows every little supernova as its own little point. But that becomes computationally expensive. And so one of the things we do is, as you say, we bin things up as we go along. It's not such a big deal for the project we're doing with Hubble constant, but as soon as you start going far enough out to measure the dark energy, the effects of dark energy, which was what led to that Nobel Prize and everything, you gotta bin these things up, and then it allows you to see precisely how the universe was evolving at every redshift that you go to. And that actually ended up being so one of the things, as I mentioned, when you measure the Hubble constant at the cosmic microwave background, and you need to know how to get that from there to what you would measure today, it turns out you can use the type 1As as a way to map that out. Now, we can only go about as far as a redshift of 1.5 or 2 so far. I'm actually hoping James Webb will let us go a little bit further over. But yeah, it's kind of like it's building a bridge between today and back then. And it's so good. It fits the standard model so well. It really makes it hard to introduce new, interesting physical things happening. you basically have anything interesting has to be pushed all the way almost back to the cosmic microwave background, or even before, in order to allow interesting things to happen and yet still fit the data that we fit so well. The universe isn't giving us a lot of wiggle room. It's very it's very annoying.
Yeah.
If you wanna-
Very perplexing. Okay.
It's
well,
very
thank you.
perplexing. Yes.
How far into the future is James Webb time booked?
Oh, that's a really good question. I think it's something on the order of 2 years. So, and that's so what they always try to do is they never want to be in a situation where they've run out of things to do. They always want to have an over abundance of things on the menu, if you like. And so when you propose, you are proposing for a particular semester. So it's a semester system. And sometimes your science can get bumped into the next semester because it took them a little bit longer to do what they were supposed to do, and so you just go along. But once you've been given time, you have that time. And the wonderful thing about space telescopes is you never lose it to clouds. So yeah, it's usually on a yearly basis.
Interesting. Thank you.
Chris, is it too simplistic to say that that evolution of the Hubble constant over time has something to do with dark energy?
Oh, that's exactly what it's due to dark energy, and it's also due to the matter content in the universe. So back in the 90s, when I was a graduate student, they were the intent of using type 1a supernovae was to measure the deceleration of the universe. No one ever thought they would measure an acceleration. They always thought it would decelerate. And the reason for that is because the universe is full of stuff, and gravity likes to pull on stuff. It doesn't like to push, it likes to pull. And so even if the universe started with a certain speed, velocity, whatever you want to call it, kinetic energy, it would eventually either, if it has enough stuff pulling, it would reach a certain size and then run out of gas, and then it would just recollapse. Or if it started with a huge amount of energy, it would just keep on expanding, but always slowing down. But kind of like when you throw a ball up, there's three possibilities. Either you throw it up, it comes back down. You throw it up at exactly the right speed that it travels on a parabola and reaches escape velocity, or you throw it with more than enough speed and it goes off on a hyperbolic orbit and never comes back. Same thing with the universe. But when they came along and did the measurement, and you had two teams doing it independently, both of them were seeing an acceleration, not a deceleration, and that made no sense. Like, why in the world would things be getting faster than slowing down? And that's where they had to reintroduce. I mean, it'd been introduced so many times before, but this time they seem to really need it. They put the cosmological constant back in order to explain this expansion. And the way the cosmological constant works in Einstein's equations is essentially, it's like anti-gravity. It tends to push things away rather than have them pull. And so, of course, we never saw that in the lab or anything like that, so we always assumed it was zero. But, it's that little extra knob you need to make it make sense. So yeah, the exact details on what happens to the Hubble constant over time is directly related to what's in the universe. What is it made of? And if it was just matter and dark matter, we should have seen a Hubble constant that was larger in the past, because it means the universe is slowing down. But we didn't. We saw a Hubble constant that was smaller in the past, and therefore it must be speeding up. And the only thing we have in our toolkit here to make that happen is this mysterious dark energy or cosmological constant, however you want to look at it.
That helps. Thanks.
Yeah. Okay, that's everything?
Well, thank you. That was really interesting.
Yes, thank you very much.
You're very
thank you.
welcome. And,
Yay!
Just another bit of announcement. So I don't know if any of you have ever been to the Carnegie Open House, but so far it looks like we're going to try and do an in-person open house this year. And let me check I believe it's going to be October let me see here, month. It's like the third Sunday in October. Yeah, October 16th, I think, is when we're going to be doing this. So if you're interested in learning more about, all the stuff that Carnegie has done over the years, plus the new stuff that we're building, we'd love to have you.
Do you think that the library will be open?
Oh, yes. If the open house, if we do an in-person open house, then the library will be open. The machine shop where we build our instruments will be open. Then we usually have a whole bunch of exhibits on the lawn, snacks, drinks, stuff like that. Lots of astronomers to talk to.
Want to have a field trip.
Yep, makes a good field trip.
A few years ago, the Carnegie Observatories were having a lecture series at the Huntington Library. Are there plans to do that again, or?
They have. We've been doing it. I have a feeling the advertisement for this, it was weird. So if you're on the Carnegie mail list, then you should have been notified that we did do the Huntington lectures this year. They're all available online to watch remotely, or you can be there in person, and the recordings are available afterwards, of course. So that will again start probably next year around, it's usually I think in May, I think we start these things. But it was weird because I work at Carnegie and I never got notified that these lectures were going. So I think the ball got dropped somewhere.
I went to 2 of them this year. I think that they were, I think it might have been in April, could be wrong, but just
Yeah.
excellent. One thing that's unique about that for the people that haven't gone is there's a recital ahead of time where you have people playing musical instruments for, I think, at least a half an hour before the lecture.
Yep.
Hmm.
It's a nice.
This doesn't have much. Go ahead. Oh, this doesn't have much to do with anything, but Laura and I went to one of those lectures once, and we went on the wrong night, and we ended up going the night they were having a Shakespeare expert do a lecture on Shakespeare. And this guy spoke for an hour on how Shakespeare used 3 words. And I only remember 2 of them. One of them was character, and one of them was figure. And I can't remember what the 3rd word was, but they were all words that could mean like numbers or letters or people. Anyway, it was pretty interesting, but we got there completely by accident.
If you open up the chat, I put in a link that I found to the Carnegie lectures that have been recorded.
Yeah, that's good.
Okay, great.
All right.
Thank you very much. That was very interesting.
Yes.
Good.
All right. See you all. Take care, man.
Okay, see you, Richard.
Thank you again.
Thank you,
Really
Chris.
nice.
You're welcome.
Yeah.
Take care.
Okay.